Well, welcome to the session Finding the Other Trig Solution. Now, before we start, I want to kind of approach this and explain why it is you even have to find another solution. Remember, essentially when you're solving a trig equation, and you'll get to a point where you have to find the inverse trig of a number. And there are theoretical restrictions on the inverse trig functions. So if you look at inverse sine, what you'll find is when you're looking for that angle, the calculator is only allowed to look between here and here, so negative pi over 2 and pi over 2, and that solution has got to be somewhere in this interval. The calculator literally is not allowed to look anywhere else, but you can. And then when you look at the inverse cosine function, again, you're only allowed to look for solutions between, in this case, 0 and pi. And the calculator is not allowed, when I say you, the calculator is not allowed to look anywhere else. And then for inverse tangent, now the calculator is only allowed to look between negative pi over 2 and pi over 2, but not including the endpoints. So because of these restrictions, you have to do a little bit more work. Now, what I'm going to be doing at first is just kind of showing you some general patterns, and then we'll do some specific examples so you can see how this works. But the general patterns are this. If you're looking at the sine function and you're solving an equation, sine of an angle equals a positive number that of course is within a valid number for sine, so it's like between -1 and +1 inclusive. Essentially, remember what you're saying. You're asking for the calculator to give you that angle for which the y-coordinate is that positive number. So visually, that looks like this. Where the y-coordinate is that number, whatever that number is. So the calculator says, oh, here, this is your rotation. So here's your calculator answer, which will be a positive angle. It's in quadrant 1. So then when you go to look for the other angle, it's also going to be answering the question, where is the y-coordinate the same length that way? It's going to be in quadrant 2. And what you want to do is basically say, this is my other angle. That is my solution. So how do you say that? You say pi minus the calculator answer. And since the calculator answer is positive, pi minus that positive rotation is going to be a little less than pi. So again, visually what you're doing is you're saying pi and then minus that calculator answer will put you right here. Okay? Then if you're looking to solve sine of an angle is equal to a negative number, then again the question you're asking is first for the calculator, for what angle from negative pi over 2 to pi over 2 is the y-coordinate negative? So let's say you're here. And the calculator says, oh, okay, that's going to be this. So the calculator will give you an answer. And that answer, that angle is going to be negative. Because again, it has to be from negative pi over 2 to pi over 2. So that answer is going to be somewhere between negative pi over 2 and 0. So it's going to be a negative rotation. So where else do you have the y-coordinate being that negative length? Well, it's going to be in quadrant 3 over here, for which you want to say, this is my rotation. Now, to go ahead and do that, you want to answer for the other, you want to say pi plus the reference angle for the calculator answer. So essentially you have to make that angle positive that the calculator gave you. Why is that? Well, though you went here, this rotation, and essentially that rotation is the same as this rotation, you want to say pi plus that rotation. Okay? So the calculator answer will be negative but you've got to make that positive and then add it to pi. Okay? So that you'll have an answer that's more than pi, more than 3.14. Then if you look at cosine, you have, for example, cosine of an angle equal to a positive number. So again, you're asking the calculator, give me that angle between 0 and pi for which the x-coordinate is positive. So let's say the x-coordinate here is positive. And the calculator say, there it is right there. There's your angle, there's your rotation. So that rotation is going to be positive. And then the other place on the circle where the x-coordinate is positive is going to be here, down in quadrant 4. So you then want to say this rotation. So it's just going to be, for the other solution, the negative of the calculator answer. And then when you want to know cosine of an angle equal to a negative number, you're asking the calculator for what angle between 0 and pi is the x-coordinate, the length of that negative number. So that might be something like that. And the calculator say, oh, here it is, and this is the rotation it'll give you. So the calculator answer, it will be positive. And then you want to find the other solution, which is going to be here in quadrant 3, and it's going to be the same rotation, but it's negative. So the other solution is going to be the negative of the calculator solution. Okay? And then finally, tangent. What are the patterns for tangent? Well, if tangent of an angle is equal to a positive ratio, remember what's behind this is the ratio y over x now. Not just one coordinate, but it's the ratio of two coordinates. So if it's going to be positive, what you want to think is that y over x could have been positive because you had positive over positive equals positive, or because you had a negative over a negative is positive. So the calculator is going to give you an answer in quadrant 1, because remember tangent is restricted to negative pi over 2 to pi over 2, and so you have to be in quadrant 1 if the ratio is positive, which means you must have had a positive x and a positive y. Put you here, this is your angle, the calculator gives you this rotation here, which will be positive in itself. Your other movements will be the same, but they'll be negative, so you'll be out here negative x and negative y, which will put you here in quadrant 3. And essentially, to get that other solution, you'll just say pi plus that calculator answer, and that is indeed what you want, because it's pi plus that reference angle, which is positive, but so is your calculator answer, so you're good there. Finally, when you look at tangent of theta equal to a negative number, again, remember the ratios. You could have had y over x be positive over negative, which would have been negative, or you could have had negative over positive, which would be negative. Now, from the point of view of calculator, the answer has to be in quadrant 4, which means you must have gone positive x, negative y to be here. So that's the calculator answer. That will be a negative rotation. That's how it'll give it to you. So you're looking for something where you had the same lengths, but negative x and positive y. So that puts you over here in quadrant 2. Again, 180 degrees away. So you can say this is going to be pi for the other solution, plus the calculator solution, which would be fine, because the calculator solution will be negative. So essentially, you're looking for this rotation, but it'll be after you've gone pi and then backed up that calculator solution. The calculator solution is negative, so it'll put you at something less than pi, and it'll put you here. So that'll be good. Now let's go ahead and go through some specific examples. So, example 1, sine of theta equals 0.85. So theta itself is inverse sine of 0.85. And the calculator will give you 1.5 1.0160. So that means it's answering the question, where's the y coordinate? Positive 0.85. And that's this rotation where the y is 0.85. The rotation is 1.0160 radians. So that's this rotation is 1.0160 radians. Where else do we have that? Somewhere here. And obviously this is also 1.0160 radians. So for the other solution, you want pi minus 1.0160. So that's 2.1256. Then, example 2. Sine of an angle is negative 0.85. So again, theta is sine inverse, negative 0.85. And theta will be negative 1.0160. So again, it's telling you that where's the y coordinate? Negative 0.85. Well, that's over here, this rotation of negative 1.0160 radians. So where is it that the other solution is? It's over here. That would mean where the y is. Here's the y at negative 0.85. And the rotation I'm trying to say is all this rotation here. Now remember, my calculator answer is negative. So remember, this is the one where you have to make the reference angle. You have to use the reference angle because you want pi plus that angle. So you're going to say pi plus 1.0160. And that'll be your other solution as opposed to your calculator solution. All right, let's take a look at cosine. Say the cosine of an angle is 0.4, so theta equals inverse cosine of 0.4, and theta itself is 1.1593. Now again, calculator answer is going to be, where is it that x has a length of 0.4, and that's going to be over here. The calculator answer is going to be this rotation, which is 1.1593. Where else is it that x is that length? Down over here in quadrant 4. So that's the same rotation, but in the negative direction. So the other solution is negative 1.1593. Example 4. Where is cosine of an angle? Negative 0.4. So you're asking the question, where is the x-coordinate? A length of negative 0.4. The calculator can only give it to you the first answer between 0 and pi. So somewhere here, it's going to say right there. This is the rotation, right? And by the way, sorry, if you actually look for theta, theta is going to be the inverse cosine of negative 0.4, for which your calculator will tell you 1.9823, which makes sense. It's a little past the 90 degree or 1.57 radians, so that makes sense. So your calculator will say 1.9823, and you now want to find the other place on the circle where the x-coordinate is negative 0.4. That's going to be over here in quadrant 3, where that rotation is the same amount, but it's in the negative direction. So it's negative 1.9823. And finally, for the tangent. Let's say tangent of an angle is 3.2. You're looking for the inverse tangent of 3.2. The calculator tells you 1.2679. You know that's because it's positive and positive. So you're here. This is the angle rotation right there. Calculator says 1.2679. So you want the same movements, but negative, negative. You're here, 180 degrees away. This is your other solution. And you want to say pi plus that 1.2679. Okay, so hopefully visually that makes sense. You want to do that angle plus another 180 degrees. So that's the idea. That'll put you out here. Example 6. Tangent of an angle is negative, equal to a negative number. So we have tan inverse of negative 3.2. The calculator will give you a negative angle. It has to. So you're out here at understood positive, negative rotation. So it says this is the angle of negative rotation. Here's the calculator answer, negative 1.2679. And now you want to look for same movements, but negative x, positive y. I'm here in quadrant 2. So you know your answer has to be less than pi. And so the other solution is basically pi minus the 1.2679. So in a sense, I'm just adding the calculator answer. It's pi plus the calculator answer. And hopefully that makes sense again, because you're saying pi minus that, and I'm here. Okay. So again, I've given you patterns. Work through these. Really work on drawing pictures and seeing where the angle is, and then just deciding, you can see from the picture whether you're supposed to add or subtract the angle from the calculator to get the other solution. Okay? Well, thank you very much for listening. Welcome to the session on expressing infinite solutions for trig equations. So that's when you solve the trig equations, you're going to get infinite solutions. How do you write that down? All right. Now, essentially what happens is trig functions are periodic, so they're going to be infinite solutions pretty much almost all the time, unless you have some kind of restriction that you're given beforehand. So let's take a look at an example. This is the equation y equal cosine of x, and suppose we say let cosine of theta be y, so specifically when y is a half, how do you solve that? Well, I've got a graph up here, and suppose right around here is a half. So if you look at the intersection of the cosine graph with the line y equals a half, you can see there's going to be an awful lot of solutions. There's going to be one here, so right there. There's going to be one here, so this angle. There's going to be one here, so this angle when you drop down. One here. I mean, you can go on and on and on. So there's your, this is what gives rise to your infinite solutions. So how do we handle that? Well, let's take a look. When you actually go to solve this, you would say theta equals cosine inverse, or inverse cosine of a half, and your solutions then are going to be here at pi over 3, but remember, there's another solution over here, 5 pi over 3. So this is your, what I call your calculator solution, although your calculator wouldn't really give it to you as pi over 3. Of course, it would take 3.14 or whatever and divide it by 3. Here's your other solution we've talked about. So now how do I keep going through all these? So here's the pi over 3 solution. This is the 5 pi over 3 solution. And essentially what happens, let's focus on pi over 3. The pi over 3, if you basically just look at all the coterminal angles, they're all going to be solutions. So if you keep adding 2 pi or subtracting 2 pi, you're going to get all those solutions. And essentially that's like going way over here. If you add 2 pi, this is the one you're going to get. And for 5 pi over 3, if you add 2 pi, this is the next solution you're going to get. Okay? So let's look at it arithmetically. So any coterminal angle, we're going to focus on the solution pi over 3. Remember, any coterminal angle will be also a solution. So if you take pi over 3 and add 2 pi, let's do the fraction work. Get the common denominator. So that's 7 pi over 3. And then you could say, well, that's just adding 1 revolution. What if I add 2 revolutions, or 2 times 2 pi? Then that's pi over 3 plus 12 pi over 3, which is 13 pi over 3. And you could keep going ad infinitum. Suppose I add 3 revolutions, or 3 times 2 pi. That's pi over 3 plus 18 pi over 3. So I get 19 pi over 3. So I could keep going on and on. Well, remember, coterminal angles go in both directions. I could have pi over 3 minus a revolution, so minus 2 pi, which is going to be pi over 3 minus 6 pi over 3, or negative 5 pi over 3. And I could do pi over 3 minus 2 revolutions, or minus 2 times 2 pi. So pi over 3 minus 12 pi over 3, negative 11 pi over 3. And then pi over 3 minus, let's say, 3 revolutions. So doing the fraction work. Okay, so again, you could keep doing this in the other direction, keep subtracting revolutions of 2 pi. So hopefully what you see is a pattern, and that pattern is that we started out with pi over 3, and we're adding a certain number, whole number, of revolutions of 2 pi. So, or multiples of 2 pi. So here it's understood k is an integer, and remember, an integer is a whole number, can be positive or negative. Now, generally, you can write it this way. People tend to like to write it 2k pi. Honestly, there's no difference. It's just a little prettier. Okay. Now, of course, if you did the same thing for 5 pi over 3, you would see the same thing, same basic pattern. Instead of pi over 3 plus 2k pi, you'd have 5 pi over 3 plus 2k pi. So what are your solutions? Well, I call it a generator. What we have just come up with are generators for specific solutions, but the generators actually encompass all the solutions. So I would have theta equals pi over 3 plus 2k pi, and theta is equal to 5 pi over 3 plus 2k pi. Okay, same pattern. Now again, I call these my generators. Now that's my word. That's not mathematically accepted, that's just my word. That's because now you can actually get specific solutions by substituting integer values for k. So again, we'll work with pi over the generator for pi over 3. Suppose we look at the pi over 3 plus 2k pi. Let me show you some examples of how do you get those specific solutions. Well, again, you just put integer values of k, whatever you want. You can put in 0, 500, negative 20, doesn't matter. So we'll start with some that most people would do. So you'd have theta equals pi over 3 plus 2 times 0 pi. Remember, 0 goes in the place of k. And you'll get just pi over 3. Let's try another value like negative 2 for k. So you get pi over 3 plus 2 times negative 2 pi. And you'll get pi over 3 minus 4 pi, which is pi over 3 minus 12 pi over 3, which is the negative 11 pi over 3. And hopefully you'll recognize that as one of the solutions we got. And suppose k is 3. Theta equals pi over 3 plus 2 times 3 pi equals pi over 3 plus 6 pi. So that's pi over 3 plus 18 pi over 3, or 19 pi over 3. Again, another solution hopefully you recognize. So again, though, you could keep going on and on infinitely. Okay? Now let's take a look at another example. Suppose you're looking at tangent of theta equal to negative 1.2. Alright, so when you solve this and you say theta equals the inverse tan of negative 1.2, and your calculator gives you negative 0.8761 radians. Okay, we saw, well, you can check out another session on finding the other trig solutions, but we're going to have to do that. So our first solution, which came from our calculator, was here at negative 0.8761. And then there's going to be another solution over here. So this is our calculator solution. Here's our other solution. And that's going to be pi minus 0.8761, or 2.2655 radians. Now, what you can see, though, is that once you have a solution, say we look at the calculator solution right here. So I put a little star there, calculator solution. The other solution is exactly pi away, a distance of pi. And once you're on this other solution, to get to another name for the calculator solution, is you'd have to travel another rotation of pi. So you can keep doing this, and once you're on the calculator solution, you go back to the other solution by going pi. So these solutions, the calculator solution and the other solution, as well as their coterminal angles, are basically equidistant from each other. They're pi away, and you can see that on the circle. So essentially what I would write for the generator, okay, is theta equal to negative 0.8761 plus k pi. So essentially what you're doing is you're starting with a solution. It really doesn't matter which one. In this case I picked the calculator one, 0.8761, and then you add k times the distance between them. So that's your generator here. Okay. Let's take a look at another example. Tangent squared of theta equals 1. Now I just want to point out this is the same thing as tangent of theta squared equal to 1. So therefore what I want to do to start solving for theta is to take the square root of both sides. So I want to take the square root of, and I'll go back to the first form, tangent squared theta, take the square root of both sides. And that'll give me the absolute value of tangent theta equal to, well, square root of 1 is 1. And then tangent theta is equal to plus or minus 1. So essentially that's going to give me two equations I have to solve. Tangent of theta equals the positive 1, let's say, I'll put that for emphasis, and the tangent of theta equal to the negative 1. Okay, so what we know then is theta is the inverse tangent of 1. And again, that's asking for what angle between negative pi over 2 and pi over 2 is the ratio y over x equal to 1. If you ask the calculator that, it will give you pi over 4. It'll just do it in its, give you a decimal answer for pi over 4. But essentially, you're here. The other solution is going to be over here at 5 pi over 4. And this will be the calculator solution if you put it in there. And then if you look at the other equation, tangent of theta equal to negative 1, you're looking for where is the ratio y over x equal to negative 1. Well, technically your calculator solution will be here at negative pi over 4, or you could call it, the calculator has to give you negative pi over 4, because theoretically it has to be an answer between negative pi over 2 and pi over 2, but you could say 7 pi over 4. And then the other solution is going to be here at 3 pi over 4. Okay. And so if you put it all together, here's essentially what you have. These and these. You have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And these are equidistant from each other. So you want to know, well, what's the distance from pi over 4 to 3 pi over 4? Well, subtract them. 3 pi over 4 minus pi over 4 is 2 pi over 4. And if you reduce that, that's pi over 2. What's the difference from 3 pi over 4 to 5 pi over 4? Well, subtract them. 5 pi over 4 minus 3 pi over 4 is 2 pi over 4. 2 pi over 4, when you reduce it, is pi over 2. What's the distance between 5 pi over 4 and 7 pi over 4? Well, again, subtract them, you'll get pi over 2. What's the distance between 7 pi over 4 and the next answer that you would get? You would see it's pi over 2. So these are equidistant from each other. And, or in this case, pi over 4 would be 9 pi over 4, but you'll coterminal angle for pi over 4. Eventually you'll see that these are all pi over 2 away from each other. So how do I express a generator that captures all of them at once? Well, again, start with any angle. Doesn't matter which one you picked. You could pick pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Most people would pick the pi over 4. And then you would add k times the distance between them, which is pi over 2. That is your generator. Okay? So, hopefully then, let's take a look at this generator so you can see that it really does pick up all the solutions. Let's take a look at theta equal to pi over 4 plus k times pi over 2. Let's just put in some values of k to get specific solutions. When k is 0, I get theta is pi over 4 plus 0, or just pi over 4. That was our first one that we recognized. When k is 1, theta is pi over 4 plus 1 times pi over 2, which is pi over 4 plus 2 pi over 4. And look, there's my 3 pi over 4. When k is 2, theta is pi over 4 plus 2 times pi over 2, which is pi over 4 plus 4 pi over 4. There's my 5 pi over 4. And we'll do, you could keep going. Let's just do this last one though. So you see that all of them are captured. It's pi over 4 plus 6 pi over 4 is 7 pi over 4. Okay. And obviously the next one's 9 pi over 4 and so on and so forth. But, so you see that this is, it really does work. And so your generator is pi over 4 plus k pi over 2. In general, here's the pattern for writing your generator. And this is, of course, if the solutions are equidistant. So, if solutions are equidistant, to write the generator, you start with a solution. Most people use the calculator solution, plus k times the distance between solutions. Understood where k is an integer. Okay. So then, just recapping this a little bit, the first one we had solutions here, pi over 3, and then 5 pi over 3. And when I say equidistant, well, when I look at the distance it takes from pi over 3 to 5 pi over 3, that's not the same as going from 5 pi over 3 back to pi over 3, or another name for pi over 3, the next coterminal angle. Those distances are clearly not the same. So I can't use one generator to capture all solutions that both those angles would generate. So in that case I have to handle pi over 3 separately, right? And I have to say pi over 3 plus 2k pi, and here 5 pi over 3 plus 2k pi. So in essence I have two separate generators because the solutions are not equidistant. Then, so that was our first example, right? In our second example, we solved tangent of theta equal to negative 1.2. And what we saw, we got these solutions. We got here, negative 0.8761, and we got over here, 2.2655. But we saw these are equidistant. The distance from negative 0.8761 to 2.2655, and then from 2.2655 to the next name that would be given to negative 0.8761, that distance is pi. And it doesn't matter which direction we go in, counterclockwise or clockwise, it's either positive pi or negative pi. That's why we use k as an integer. So the integers could be positive or negative. So again, the generator we got then was negative 0.8761. That's the A solution. plus k times pi. So there's k times the distance, the equal distance. Okay? And then in our third example that we did, we solved tangent squared theta equal to 1. And we saw that when we put it all together, we got here, 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 here. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Right? And that these were the same distance apart at pi over 2, pi over 2, pi over 2, pi over 2. So the generator was pi over 4 plus k times pi over 2. So there's my A solution, meaning any solution. And then you have k times the distance, the equal distance. Okay. So there's your generator. That's the pattern. And that finishes this session. Thank you for listening. Welcome to the session on solving trig equations. Now, let me just tell you that I'm assuming we're solving now some complex trigonometric equations. And you may want to, if you haven't already, take a look at first solving basic trig equations, that session, and then go to another session, finding the other trig solution, that's another session, and finally another session expressing infinite solutions for trig equations. Those are 3 sessions you probably want to look at if this is new to you. So this is going to kind of gloss over those details, assuming you already know them. So if you don't know, if you find yourself getting confused or just don't have all these details, go back to those 3 sessions before you keep going on here. So we will start with the process. First of all, always be in radian mode when you're solving trig equations. You'll see why really in step 4 where you resubstitute. But here's what I do. First I do a substitution, and that's of course only necessary if you have anything other than a simple angle. Then you do the algebra, if there is any, to solve for the trig function. That's to isolate the trig function. And at this point, in step 3, you should have a basic trig equation. Now essentially everything we do is to reduce everything down to a basic trig equation. That's how we really solve. And then you go through the 3 steps, find the calculator solution, find the other solution, find infinite solutions. And once you've got the infinite solutions in terms of your angle, now you go back and resubstitute from what you did in step 1, and finally solve for the original variable. So let's take a look at an example. -3 cosine of 2x minus 1 plus 5 equals 7. Alright, so this is definitely not a simple angle. This is, the argument is complex. It's got 2x minus 1, your angle's x, but you know, it's got all this stuff. For it to be simple, you should have just had cosine x, not 2x minus 1. So the first thing we're going to do is a substitution. And in that case, I'm going to say let theta be 2x minus 1. And so that way, when you rewrite this, you're going to have -3 cosine of theta plus 5 equals 7. So now that's what I call a simple angle. And here you're ready to do the algebra. To solve for cosine theta. So what I want to do is subtract 5 from both sides here. So I have -3 cosine of theta equals 2. And now I want to divide by -3. And that'll leave me with cosine of theta equals 2/3. And, oh, I'm sorry, -2/3 because that's a -3. Okay, there we go. So cosine of theta equals -2/3. Now I'm at basically step 3 where I have a basic trig equation. So that's kind of nice. let's go ahead and find our calculator solution. So here we're at step 3. We're at a basic trig equation with cosine theta equal to negative 2/3. That's what we're solving. So theta equals the inverse cosine of negative 2/3. And so to find the calculator solution, you just plug that into your calculator and it'll give you theta equals 2.3005. When you go to find your other solution, then remember you're really looking for where the calculator gave you that first angle where the x coordinate is negative 2/3, so that's maybe over here. And so that's 2.3005. That's your calculator solution. Now you got to find the other solution over here. And so that's going to be, if this was the calculator solution, this is going to be your other solution. So it's negative 2.3005. And so now infinite solutions. Well, these are not equidistant apart, that's for sure. So you're going to want to have two separate generators. Where k is understood to be an integer. And now, this is probably the step where it's so easy to forget. That's why I have it as a separate step. Resubstitute. So you let theta be 2x minus 1. So now, in the place of theta, you're going to have 2x minus 1 equals 2.3005 plus 2k pi. And you're going to have 2x minus 1 equals negative 2.3005 plus 2k pi. Okay? So now let me rewrite that. And I've now got to solve for x, the original variable. Okay? So we have 2x minus 1 equals 2.3005 plus 2k pi. And so here you're going to add 1 to both sides. Get 2x equals 3.3005 plus 2k pi. And now you just divide by 2. Remember, every term gets divided by 2. So you have x equals 1.6503 plus k pi. And now your other resubstitution, you add 1 also. Okay, and then divide by 2. Every term gets divided, so x equals negative 0.6503 plus k pi. Alright, so those essentially are your generators. Okay, and we're done solving. Again, I just want to show you that if you want to find specific solutions, you just basically put in different values, integer values of k. So we'll just continue on here. For here, if k is 0, obviously you're going to get x equals 1.6503. If k equals 1, you're going to get x equals 4.7919. K equals negative 1, you're going to get x equals negative 1.4913, and so on and so forth. And again, I'll just check one of these so you could see. Check the first solution on this. Your check would be to resubstitute your specific solution into your equation in the place of x and see if you get a true statement. So you'd have negative 3 cosine of 2 times 1.6503 minus 1 plus 5, is that indeed 7? And I get 7.000169973. I think that's pretty good. So again, you can do this for each of these specific solutions and prove to yourself that, wow, okay, this really does work. I've got the right solutions. I have found that to get the kind of accuracy you need to really recognize that you're getting the right answer, you have to go out about 4 decimal places. Going out less, you could actually have solved the equation correctly, but you can actually be far off enough when you plug it in that you can't tell. So I would go out 4 decimal places. Okay, we'll do a few specific solutions here. And we'll do these substitutions. So x equals negative 0.6503, k equals 1, x is 2.4913, and if k equals negative 1, I get x equals negative 3.7919. Again, these are just integer values I picked. You could have picked any integer value you want. Okay, so that's our first example. Now let's go ahead and look at our second example. And that's going to be 6 minus 14 sine of 3 pi x minus 4 equals 9. That looks nasty enough, doesn't it? Alright, so number 1, substitution. Alright, so obviously you've got a very complex argument. The argument is what's coming into the sign. The argument is 3 pi x minus 4. You really need it to be simple. So we're going to say let theta equal 3 pi x minus 4. So then, in part 2, you're solving for the trig equation, or the trig function. So you have 6 minus 14 sine, now it's just theta because of your substitution, equals 9. And that's a lot easier to handle. So now we're going to solve for the trig function itself, which is just the sine theta. So we're going to have to subtract 6 from both sides. We get negative 14 sine theta equals 3. Now divide by negative 14. You'll get sine of theta equals, negative 3/14. Alright, so now you're here. This is a basic trig equation. So now you want to work with your basic trig equation. We now have a basic trig equation. And the first part you want to do then is find the calculator solution. Okay? So when I go to solve for that, theta is the inverse sine of negative 3/14, for which the calculator will tell me theta is negative 0.2160. So then we want to go and find the other solution. So the other solution is, again, you're looking for where the y-coordinate is a length of negative 3/14. So let's just say here. And so this would be, this y would be negative 3/14. So the rotation itself, though, is negative 0.2160. This was the calculator solution. So you know you've got another solution over here that you've got to name. And that's going to be pi plus 0.2160. Remember, this is the case where you have to work with the reference angle and make that reference angle positive, because you want pi plus the 0.2160. Gives you 3.3576. Obviously, these are not equidistant apart, so when you go to find the infinite solutions, you're going to have separate generators for each one. Theta equal negative 0.2160 plus 2k pi. And theta equals 3.3576 plus 2k pi. Finally, step 4, well, not finally, but this is a real important step. Remember, it's the one I even write with an exclamation point. So you're going to have 3 pi x minus 4 equals negative 0.2160 plus 2k pi, and 3 pi x minus 4 equal to 3.3576 plus 2k pi. Now you're going to solve for x, for the original variable. So 3 pi x minus 4 set equal to negative 0.2160 plus 2k pi. We're going to add 4. We have 3 pi x equals 3.784 plus 2k pi. Divide by 3 pi. Every term gets divided. And you'll arrive at x equal to 0.4015 plus 2/3 k. That's for the first generator. Second generator, 3 pi x minus 4 equals 3.3576 plus 2k pi. You add 4. You get 3 pi x equals 7.3576 plus 2k pi. And now divide by 3 pi. And you get x equal to 0.7807 plus 2/3 k. And that's it. So, those are our 2 generators. Again, if you want specific solutions, just substitute values, integer values for k, and you'll have all the solutions you want. Thank you so much for listening.